photoelectrons which is to be constituted. You can easily observe that. Okay. So here, what are the experimental observations which is to be noted here? So there is a for a given material, there is a minimum photo energy. That means photo energy means here you have to be talking about the here E equals to h nu. So that the photo energy is h nu naught, which is the characteristics of the metal here. So for h nu naught, no photo electrons would be released by the radiation of frequency less than that of the nu naught. That means you have to increase the frequency here. Okay. So at what frequency the photo electrons which are to be not emitted by this metal plate, that frequency is nothing but a threshold frequency. You should remember that. Okay. And later on, if the electrons which are to be emitting by the photo metal plate, so you have to imagine that the electrons which can processed by the kinetic energy. So simply you have to say that the kinetic energy of the emitted photoelectrons, which can vary from the 0 to the maximum, that is the K maximum, K which is related to the kinetic energy. So which is also depends upon the incident photon energy as well as the work function of the material. And these are independent of the intensity of the light. Next one. So the photo current, which is always directly proportional to the light intensity. Just now we discussed that. If the intensity more photo current. If intensity is less current is to be constituted. Next, photoelectric emission, which is a phenomena which is an instantaneous. That means there is no time lag between the irradiation as well as the emission. And the phenomena is a random phenomena. That means here sometimes it may be increases, sometimes it may be decreases here, not in a continuous manner. So random phenomena at any particular instant, only among the millions of atoms of metals will emit from the photoelectrons. Now, not to be said that only single electron is emitted by the metal plate or only 2 electrons. So millions of electrons which is to be emitted by the metal plate. So here the classical electromagnetic wave theory of radiation, which is found incapable of explaining the which experimental facts which are to be there. So there should be a satisfactory explanation about this. We have to restore and altogether a new idea, which is known as the quantum theory of the radiation. So this may be asked as a short question, but the thing is that you have to explain about the here what is the work function equation here. So just now we discussed about that Einstein proposed the quantum theory of photoelectric effect. In which year? 1905. So which is closely related to the quantum theory of radiation. So the quantum theory of radiation, who was proposed? Max Planck. Okay. So Einstein considered that Planck's requirement of the energy content of the electromagnetic waves of the frequency, which is having a nu here, and there is a radiant source which can have only 0 h nu. That means 1 h nu, 2 h nu, 3 h nu, like that nh. So that means the energy can be divided into these categories. So that here from the another energy state is there, minus 180 h nu. So here where the velocity of the light is here spreading in all directions here, you know that. So you have to assume that the energy content capital E of the bundle, which can call it as a quantum of energy, which is related to the frequency h nu here. So you know that E equals to h nu, where E is the energy, h is the Planck's constant, mu is the frequency. So you have to derive the here what is the work function value here. So Box model of metal crystal indicating a photoelectric emission where it is to be takes place here. I means here inside and O is the outside. Here the S is the source here. That means here which is a crystal surface. That means whenever the light which is to be incidenting upon the crystal surface, you have to imagine that there is a photoelectrons which is to be here emitting by this surface here. So you have to imagine that, which is You have to know that photoelectric emission which can take place, that means E is greater than the EF, that means Fermi energy value, okay, plus work function W, that means here uh, W, which is the work function of the metal, which can define that how much the amount of energy which must be exceed the EF, so that the electrons which can escape from the metal surface, and also the electron having the energy inside that EI in the crystal or the metal, whatever it may be, which is to be absorbed such energy which is in the form of H nu. Then only the electron which is to be escaping from that metal surface with such a kinetic energy, so that the value which should be K equals to EI plus H nu minus EF plus W work function is there. So this is the case. And also here for a photons the given frequency equals to H nu, kinetic energy of the electron which is the largest, then the internal energy is also large. So what is the maximum value? EI is EF. Simply you can substitute in place of EI. What do you say here? The kinetic energy of the electron is largest when its internal energy is large. If more internal energy, more kinetic. That's why here EA equals to EF here. So that the Fermi energy level EF value, EF plus H in above equation substituting, EF get cancelled, remaining is H nu plus W, or you know pretty well kinetic energy formula half m square, substitute equals to half m square equals to H nu minus W. So this is a Einstein photoelectric equation. And also you have to imagine that the velocity of the photoelectron which is directly proportional to the frequency of the radiation, and also independent of the intensity of radiation, and the threshold frequency varies with the nature of the emitters, and there is no time lag in the process. Okay, so this is about the frequency to the kinetic energy. When the frequency increases, the kinetic is also simultaneously increases. After the threshold frequency, at the threshold frequency, there is no radiation. That means here there is no emitting of the electron which takes place. That's why the graph is also indicating that at such a frequency, then only the alkali metals which is to be emitting. Before that threshold frequency, which is always a negative. At what frequency? At what frequency? Here the kinetic energy value, and that means the kinetic energy of the photoelectrons is 0. That frequency you can call it as a threshold frequency. This is a nu naught. That is not to be shown in the figure. You should remember. Next, Compton effect. What is Compton effect? Most important. In this chapter, you may expect the photoelectric effect or else Compton effect. Either any one of the concepts, questions is used to be given to you. Next, what is Compton effect here? A.H. Compton. Okay, his full name is A.H. Compton. He is a scientist. He discovered in 1923 that when a beam of X-rays, okay, what do you say? A beam of X-rays of well-defined wavelength is lambda naught is scattered by a metal. Scattering means where whenever it is to be incidenting, so that the spreading of the rays in all directions, you have to say that scatter. Okay, so that such a X-rays which are to be incidenting upon a metal plate, a beam of X-rays which is to be incidenting upon that metal plate, so that these X-rays having such a frequency lambda naught, okay, initial wavelength, so that these are to be scattered in all directions, so that the scattered angle is theta to the incident radiation, so which is to be found to contain a component well defined wavelength lambda naught, which is longer than that lambda naught, so that this phenomenon you can call it as a Compton effect. So this is also with the help of the electromagnetic radiation. You can see that here, Compton setup. So this is a target tube is there, so that the X-rays from the X-ray tube, capital T, which is to be emitting X-ray tube, there is a metal plate is there. Okay, so that means QT, which is to be strike graphite block. What is that block? Block is a graphite block. When it is to be hitting there, incidenting there, scattered in all directions. So the target of X-ray tube was here molybdenum. So what do you say here? That is a molybdenum which is to be takes place in the X-ray tube. So that the wavelength K alpha or Ka wavelength is here, which is you say which is 0.708 angstroms. So that the monochromatic radiation which was employed in the scattering experiment. So you can see here. So P is a radiation tube. What is the P is a primary time and the S is the secondary time. Before that and after the scattering, before scattering and after scattering, where theta is the scattering angle, P is the Bragg spectrometer. There only you are going to be finding there. So that you have to imagine that. So at theta equals to 0 degrees, how the peak is to be observed, lambda naught incident, and theta equals to 45 degrees, there is a change, and theta equals to 90 degrees, two peaks is to be observed, and theta equals to 130 degrees. Here, increasing the lambda values, so that how it is to be takes place here. That is to be noted here. So there is a shift which is to be takes place between the wavelengths. That is the lambda, delta lambda naught, which is nothing but here. Lambda naught minus. Actually, you need not to say that lambda naught minus lambda theta. Lambda theta minus lambda. Okay. So this is theta. So which is representing here shift in the wavelength of the incident rays. As a result, scattering was found in increasing the theta, and also which is independent of the lambda naught. Also, the nature of the scattering. So you have to know that what is the classical theory of the electromagnetic wave, and wave frequency nu naught, which is to be interacting with the electrons in matter, so that it is to be oscillating electric field, which can drives the electrons in forced vibration at same frequency, and these vibrating electrons irradiate the absorbed energy in the form of electromagnetic waves in all direction with this frequency nu naught. So hence the classical theory cannot account for the observed modified Compton effect. Only the existence of the line M, the scattered radiation, was accounted by the quantum. You can easily observe that how the scattered radiation takes place. Okay, H nu naught is the incident radiation. Later on, there should be here with the theta and as well as the pi angles, which is to be how the scattering is to be takes place. So you have to calculate the values. Okay, origins. You have to derive the equation applying the principle of conservation of energy of collision before and after. Okay, before is initial H nu naught. Later on, after this H nu theta plus kinetic energy of atmosphere. So by applying the relativistic theory, which is also proposed by the Einstein, okay, so you have to simplify it, and you will get the equation P equals to E by C or H by C. Okay, momentum. So that is to be calculated. Most important. And also you have to calculate the what is the scattering angle here. You have to notice that what is the shift in the wavelength lambda theta minus lambda naught equals to, which is nothing but a lambda delta lambda. That value should be h by m naught c. H is the Planck's constant. M naught is the here reduced mass. That means rest mass of the particle. C is the speed of light. So 1 minus cos theta. H by m naught c into 1 minus cos theta. Okay. So here you can experimentally as well as theoretically, they are going to be here comparing and coinciding that whether The experimental setup which is to be giving out the theoretical values or not. So successfully they have been calculated the values. This is the case. Next, the dual nature of light. Yesterday we already discussed that. According to the Newton corpuscular theory, classical theory, later on Huygens wave theory, quantum mechanics, which is to be says that how you have to write it. Next, what are matter waves? Sometimes matter means it consists of mass. Okay, so how the matter waves when the radiation sometimes display in a characteristic of particle. The particle is there, definitely which causes it is having such a mass and velocity, momentum. Okay, why not matter like this sometimes display in the characteristics of waves? So that so many experiments have been done on this concept here. Later on, de Broglie, he was developed the here to the process which the postulates of matter waves. According to that, E equals to h nu later on, E equals to mc square by coinciding. They have been calculated h by lambda equals to. Or lambda equals to h by p or h by p means momentum, mass into velocity. Next, Davison and Germer. This is also important. So here there is a similarity between the X-rays and the de Broglie waves, which was suggested by the method of experimenting on the diffraction of X-rays could be extended to matter waves. In 1927, D.J. Davison and Alan Germer, they have been performed an experiment using the beam of electron instead of X-rays. A tungsten filament is to be considered, yeah, which is to be heated. When it is to be heated, electrons which is to be emitted, okay, and also which are to be accelerated by the potentiometer. That means potential difference V, and then the electrons which can escape and moving towards the plate. Okay, so that the electrons possesses the kinetic energy, which should be measured in the form of an electrovolt, the form of fine panel pencil. So that this should be act like an electron gun. That means a beam of electrons which is to be passing through that, and which falls on a crystal here, a single crystal. Let's see. So entire process which is to be enclosed in a vacuum chamber, and the reflected electrons which is to be collected by the detector D, and which is a Faraday cylinder. Again, this cylinder which is surrounded by the another cylinder which is to be recording this. This is the process. Okay, you need to draw this figure, Davison and Germer. IB the incident beam, F is a filament here, which is to be connected to the potentiometer. Potential, increasing potential, emitting of electrons. RB means the reflected beam. C is a crystal is there that is to be emitted by the electrons, and these are to be that means the filament there only which can send the electrons just like a electron gun, so that a continuous flow of electrons which is to be targeted by the crystal C here. So there is a detector is also there which is to be detecting that how many of the electrons which is to be emitting from that metal plate. Okay, so this is about. And also you have yes, Bragg's law, lambda equals to n lambda equals to 2d sin theta implement is there. Here also experimental theoretical calculations they have been performed. Next, Thomson and Wright experiment is also. Yeah, relationship between different velocities. So how do you relate the group velocity and the particle velocity? Here V is the particle velocity, G, VGW, the velocities of the particle group wave. V means particle, G means group, W means wave velocities. Okay, lambda is the wave. So that what is the here group velocity of the system? It's consisting of a number of waves which is to be found to be equal to G value equals to W minus lambda. That is nothing but a dW by dt. So in free space, that should be equal to 0. If it is 0, then G equals to W. Okay. So we have to do that and we have to write it down. Most important short question. You have to be calculating that what is the relation between the group and the velocity and next the relationship between the group velocity and wave velocity. W equals to lambda, and lambda according to the wave velocity, de Broglie's theory h by mv, that T, it is to be in place of V, you are writing mg, dt, then kinetic energy is of mg square. Okay, so you have to be simplifying these equations. You need to write it on the W equals to G by 2. Okay, that means wave velocity or the phase velocity is the half of the group velocity. W equals to D by 2. Next is the uncertainty principle. So your position and momentum of any particle at a time you cannot be able to find out, estimate. So that this is an experiment which was to be given. Delta x is the change in the position. Delta px is the momentum which is to be equals to the h, which is the Planck's constant. Okay, or else you have to write it down. It's cross by 2 pi also. No need to be worried. That is so. Consequences. Sometimes they may be asked, what are the consequences of the uncertainty principle? So they have been showing that the delta E, the uncertainty energy at the time delta T. So then delta E to delta T is approximately equals to h cross. H by 2 pi. So momentum plus of energy. That will be right. There is a problematic question also. Okay. Summary: how the emission of electrons by a metal plate according to the photoelectric effect, and who observed, who discovered this, and who gave the explanation of this phenomena, the basis of Max Planck with the help of quantum theory of radiation, and they have been calculated the work function, kinetic energy, h nu minus w, photoelectric equation, later on Compton effect. Okay. Native. Later on Compton effect. Then they have been demonstrated the particle nature of electromagnetic wave radiation and corpuscular theory. What is corpuscular Newton corpuscular theory? Huygens wave theory. What is the dual nature of the electromagnetic radiation? Later on, de Broglie's theory. Davison and Germer's, which is to be fall on a nickel or crystal, observe the intensity of the effect in different angles for the different energies, and which can gives the shows that uh, the value which was measured, they will have close agreement with the value collected. Okay. In unified physics, you can easily next Thomson rate and matter waves, relation between the group velocity, phase velocity, wave velocity, which is always equals to the half of the group velocity 3 by 2 and Heisenberg uncertainty. Okay. What are the expected questions in this? Is that photoelectric effect and Davison and Germer experiment, Compton effect. Okay. So these are the three questions. So out of these three, one question is to be carried out. And the short questions is that uncertainty principle and wave velocity, group velocity, and limitations of the uncertainty. You can go. These are the problems. Next is the Schrodinger wave equation. So in this, we will give you introduction about the Schrodinger wave equation and also what are eigenfunction as well as the eigenvalues. If you want to understand the wave function and its interpretation to a particle in a proper way, which can solving the different types of problems using the wave mechanics. Here, uh, scientists give different types of interpretation for the wave function. And, three of them were found much useful to explain about the experimental facts in the physics here. Schrodinger, he have been introduced a mathematical function, psi, wave function. Okay? Psi is a wave function, which is the variable quantity, which is associated with the moving particle. Okay? And also which is a complex function of the space coordinates of the particle and time. Then psi is called the wave function as it characterizes the de Broglie wave associated with the particle here. The Schrodinger wave equation, which is a fundamental equation of the quantum mechanics, like Newton's second law in classical mechanics, F equals to ma. So here the potential energy does not explicitly depend upon the time here. So some of the forces that are acting upon this the potential energy, which depend only on the position of the particle. So under these conditions, Schrodinger wave function, psi of x comma t, x is a position, t is a time. So psi is a wave function which is associated with the particle. Okay, which can be written as the product of the. So let you know about the what are the Schrodinger wave equations. The quantum or a wave mechanics has its but when the problem of the atom could not be adequately solved by the existing semi-empirical theory of Niels Bohr. So what are the basic concepts of formulating the quantum mechanics? And also is the wave which behave like behavior and the resulting wave like properties of the particle. So with the aid of the different mechanical tools of the Bohr, Max Born, Heisenberg, Schrodinger, and other, they have been interpreted the theory of the quantum mechanics. And Max Born and Heisenberg, they have been selected the matrix for their interpretation and also mathematical interpretation. It was given by the Schrodinger and based on the replacing of the equations of motion of classical mechanics with the wave equation, which was described by the sum of the properties of the matter in certain wave process is the sense of the d properties. Therefore, the Schrodinger wave equation plays the maximum role in solving many of the problems in atomic physics. What is the independent wave equation? Let us consider a particle which is moving freely along the x direction. The mass and the speed is m and v, momentum is there, kinetic energy is also there. So the total energy is of m square, that is nothing but a p square by 2 energy there. So implementing the de Broglie p equals to h by lambda, e equals to h nu. So that if it is to be a wave is associated with the particle, so that the frequency is nu, wavelength is lambda, which is a traveling wave can be represented by a function psi, so that psi equals to a cos omega t plus phi, like that here a1 cos 2 pi x by lambda minus nu t, and which is to be reflecting in opposite direction, which can be represented here a1 cos x by lambda nu t, so that by adding these two, to be getting here the product of the two terms. So by differentiating, it will be getting like this. So final equation. Okay. So that is not a 3m, that is 2m. Please correct this. S square by 2m, not a 3m. Okay, now? Please correct. And as well as the time dependent wave equation is also there. It is to be depending upon the time here. Energy is to be considered here h nu. 2 by h cross h value cross by 2 pi. By substituting these values, you are e equals to here psi h cross p square. Also del value is to be considered here. Okay, so this is about the what are the eigenvalues and eigenfunctions, which can state the equation to solve the eigenvalues, and also the corresponding wave functions is known as eigenfunctions. Okay. What is the significance of the wave function? Millikan's interpretation, Schrodinger interpretation, Born's interpretation, volume integral, modulus of psi square dx divided dz. This is the volume. Most important object of it is Born's interpretation. It is normalized, it should be equals to 1. When this value is equals to 1, then you have to say that the probability the psi is to be normalized. So by tomorrow's class, we will discuss about the applications of Schrodinger wave. Coming class. Okay. So by coming class, we will discuss about the here applications. That means one-dimensional box, two-dimensional box, three-dimensional box. So there you can implementing the Schrodinger time-dependent as well as the time-independent equations. There also how you are going to find a particle in a one-dimensional box, or else in a two-dimensional box, or else a 3D box. And refraction coefficient, transmission coefficient is also to be noted here. Okay, that is also to be calculated. Okay, Randy? So that means by next week we will discuss about the applications of these Schrodinger equations. Okay, right, all the best. Emma Adilakshmi, any doubt regarding this? You can ask.
No, sir. No, sir.
Right. Okay. So you just focus on that where is in which chapter or which unit they are going to be asking as an essay question, and they are going to be asking as a short question. You should be focused while you are going to be doing the calculation part and also theoretical part. If you are unable to understand this, you can call me at any time. so that we can discuss.
Okay.
Okay. Right. All the best.
Thank you, sir.
Right.